got a good one for you today. Today I'm going to fall. We're going to do some stuff with triangles. Ah! All right, so today we will understand how to identify angle, similarity, and side, similarity. I will learn how to use these similarities in a real-world context, and then you'll use this knowledge to identify missing measures are similar. So, we're going back to our old friend, similarity. Hopefully you remember that similar figures have the same shape, but maybe different sizes. Two triangles are similar if their corresponding angles are congruent and or the lengths of their corresponding sides are proportional. So when we're looking for similarity in triangles, children, we're looking to see if their angles are congruent, and we're looking to see if their sides are proportional. And that gives us two different theories that we can use to check to see if triangles are in fact similar. The first one is known as angle-angle similarity, AA for short. The other one is known as side-side-side similarity, SSS for short. There's another one called side-angle-side. We don't do that in this class. You'll see that in geometry. For this class, just know that we're dealing with angle-angle, side-side-side. Angle-angle says this. Two triangles are similar if all of their corresponding angles are congruent. So if you look at triangle A and look at triangle B, are those two angles congruent?
Yes.
What about these two?
Yes.
And these two?
Yes.
Remember, it's corresponding angles. So it's the same angle depending on how that triangle's orientation is. So if we take this one, I want you to look at this. We have a right angle here. If we take this triangle and we flip it kind of like that, crudely drawn, you have to identify which angle corresponds to which. Well, these correspond, that's the right angle. You kind of have to identify which one corresponds with which angle. So just keep that in mind when you're doing it. Match up all the angles to see if they're corresponding. If they are, then they are similar to each other. It's very important. You know what this little squiggly line means? It kind of looks like that. It means that triangle A is similar to B. The way I remember this, it kind of looks like a weird S. If you kind of look at it, you turn it, flip it, reflect it. But that little squiggly line means that triangle A and B are similar triangles. We're going to get into angle-angle in detail in a second. The other one that we're going to deal with today is known as side-side-side similarity. Why are there three sides?
Because three sides to a triangle.
Because there's three sides to a triangle. That makes pretty nice. And it says that the sides must be proportional. If you remember back when we were doing dilations, to find the scale factor, we would take each vertex and what would we do with it? We divide it. We're doing the same thing here. We're taking all of the corresponding sides, such as the bottom side here and the bottom side here, and we're finding their ratios, which means we're dividing them. It doesn't matter if you put the smaller ones on top of the bigger one on top of the smaller. For me, I always like to take the larger triangle, use those as my numerators, take the smaller triangle, use these sides as my denominators. Anybody have a reason why I do that? Anybody know why?
Is it going to be easier to divide?
Easier to divide, we'll usually get whole numbers as opposed to what?
Fraction.
Fractions or
Decimals.
decimals. So what we do is we take the bottom side of this triangle, bottom side of this triangle. This is the larger one, so that's my numerator, 30 over 10. If I divide 30 by 10, what do I get? 3. These sides, if all the ratios are the same, are proportional. Does it matter if just two are the same?
No.
Has to be all 3. So you got to check all 3. So we'll check the left side of the triangle. I have 5 and 15, so I put 15 over 5. That gives me 3. I check the last one, 15 over 5. That also gives me 3. Are the ratios all the same?
Yeah.
Yes. So these two triangles would be similar. Triangle C is similar to triangle D. So there's two ways to do it. The angles or the sides. Now this seems pretty easy and straightforward. However, you're not always going to be given all of the angles or all of the sides. So you're going to have to find them first before you can identify whether or not they're proportional or congruent. What's up?
Can't you just, in order to like find if they're congruent or similar, can't you just look at the side right next to it if they're parallel?
What do you mean if they're parallel?
Like, well, not parallel, but like if they're opposites on each other and if they're like the same size, can't you just check if the angle there is that way?
But wouldn't you need the measure or wouldn't you need the angle? And if you don't have that angle, how would you get it without a protractor or a ruler? And certain things may not be drawn to scale. Why is math so hard? Tears. 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 Yes.
Can you add both angles and then subtract it by 180 to get the other angle?
Yes, you can. That's how we find missing angles, and we'll use the same similar process to find missing measures of similar triangles. Now keep in mind, think about this. How would you find the missing measure of a similar triangle? Well, if we know that they have to be proportional, think about this clearly, we'll come back to it at the end. What could you set up to find a missing measure?
Say equal to 180.
What's that called?
Proportion.
Remember how to set up proportions? Some people are like, wait, I've heard of this thing, sir. A proportion, yes. I remember the proportions. In the way back, in the long ago, in the before time, before this lesson started, I might have remembered it. But now, please, sir, share your wisdom. Tell us, what is a proportion? I will at the end. Right now, any questions on this slide?
No, sir.
No? Then, 4, 3, 2, square root of 1 is 1. So, let's dig deep into angle similarity. So using angle similarity, as I stated previously, we can identify whether or not two triangles are similar. And digging even deeper, we're told that if two of the angles of a triangle are congruent, then that means automatically the third one must also be what? Congruent. Think about it. If I have two triangles, and let's say that this is 100, and this is 100, and this is 40, and this is 40, these two angles can only be one measure, right?
Yes.
They have to be 40. So that means if you know two angles of a triangle, they have to be congruent, because the third one has to be the same, because they always have to equal 180. So we can use that knowledge to help us identify whether or not two triangles are congruent. Here we have two triangles. We have ABC and we have DEF. Right now, the measures of the angles that we're given would not lead us to believe that they are congruent. We're told that this is 100 and this is 100. We're told that this is 45 and this is 35. So right now on the surface, it doesn't look like they're congruent. However, if we use our knowledge from the previous lesson and go back in and solve for that missing angle, we may or may not be able to determine whether or not these two triangles are actually congruent. So let's identify the third angle here. From the last lesson, you remember, we're dealing with the inside of a triangle, so we set this equal to 180. So x plus 100 plus 45 equals 180. Combine your terms. X plus 145 equals 180. Subtract out the constant, and that's going to leave me with x equals what? 35. So that means that this angle equals 35. Do these triangles have two congruent angles? At least? Yes. If you wanted to keep working, you wanted to solve for this, you would find out that this triangle, this measure of this angle is what? 45. You don't need that, because once you identify that two of the angles are congruent, it means that these triangles have to be similar. So ABC is similar to DEF. We only really need two angles when we're dealing with a triangle, because if two of the angles are the same, the third one must also be the same. It's math, man. Science. Math. Okay, so let's try to work with this one. Let's go to Valentina. Here, we're given two triangles. We have ABC and DEF once again. Different measures. ABC, we're currently told that this is 41, this is 30, this is 109, and this is 30. We don't have two congruent angles. What we can do is solve for angle B to see if we get a match. It's the match game. So you set up an equation like this. We don't know what this is, so we make an x. We combine our like terms. We get x plus 71 equals 180. We subtract 71 from both sides. So Valentina, what would the measure of this missing angle be? Let her do it, please. Some people are like, I know. At you. Don't worry, she's got it. She's doing 180 minus 71. She's gonna do the equal sign and she's gonna tell me a number. She's doing it on paper. Totally fine.
Oh, hello.
Hello, Megan.
She realized she has a piece of technology. Speeding up the
109.
process. 109. So x equals 109. Do we have two congruent triangles? Do we have two congruent angles now? Yes or no?
Yes.
Yes. So are these triangles similar? Yes or no?
Yes.
Yes. So triangle ABC, once again, similar to triangle DEF. All you need is two, baby. That's it. You get two. The third one gotta be congruent. Okay. So let's go to Maria. Sliding from one side of the room to the other. Maria. So here, we're given this 70 and 58, 70 and 49. Right now we only have one measure that's congruent, 70 and 70. So we have to identify this measure to see if these triangles are similar. We set up the equation x plus 70 plus 58 equal to 180 because inside the triangle gives me x plus 128 equals 180. I subtract 128 from both sides. What do you get? I get 52, which means that this is 52 degrees. Did I match it over here? Yes or no? Did I match it? No, I have 70, 52, and 58. Is there any way that these triangles can be similar now? Yes or no? No, they can't. Because I know all three angle measures here. And I know that this is 49 degrees. If I were to go and solve for this, I would find out that this was 61, but I don't have to. Because once I find these three angles, since it does not match to this one over here, there's no way they can ever be similar triangles. These triangles are not similar because all of their interior angles are not congruent. Make sure you write in the word not to your notes. So if you find that missing measure and it's not congruent, you ain't gonna have two, definitely not gonna have three congruent angles. Not similar, baby. It's not. Questions? Questions? Hercules. All right. So using SSS similarity means side, side, side. I think of math, I think of SOS. That means help me. But I'm gonna allow you to help yourself. So we said that SSS means that the ratios of all the corresponding sides must be proportional. So we're presented with this triangle here. XAS, KGZ, whatever you want to call it, doesn't really matter. You need to identify the corresponding sides. It doesn't look like there's any reflections or rotations going on here. It looks like they have the same orientation, which means that this side, or 32, would correspond to what side over here? 8. So this is the larger triangle. Smaller triangle, I put 32 over 8, and I divide. What do I get? 4. Okay. Do I need to check the rest of them, or I can just stop right there?
Check the rest of them.
Okay. We'll see. We will see. So once again, next fraction, 48. That's going to be a numerator or denominator? Numerator. Larger triangle. Doesn't really matter. I like it, but if you used 32 as your numerator, you must use all of the larger triangle measures as numerators. If not, you can get some wacky answers. So 48 goes over what?
12.
Simple enough. We divide that. That gives me 4. And then I'm done, right? I don't need to do the last one.
No, you
I can
got
stop right there. Should I do the last one?
Yeah.
Okay, well let's see. So, let's go to Roman mode. Tell me, what is this fraction, Roman?
36 over 9.
36 over 9, and dividing that, just Roman gives me
3. I mean, sorry.
is 4. So, 4, 4, 4. That means the ratios are proportional, so the triangles are similar. All the sides are proportional, the ratios are congruent, I should say. So that means that XQS is similar to KGZ. All the ratios were the same. The sides are proportional. So that one's pretty easy, but if we look down here at this one, you have to be very careful when identifying the corresponding sides. As you can see, I've taken this triangle and I've kind of flipped it around. So you have to identify all the corresponding sides carefully. Some of them are easier, some of them are a little harder, such as, let's go to this one, 45. What's going to go beneath 45?
5.
5. That was pretty simple. 45 divided by 5 gives me 9. And then I want to identify another one. So I look at 21. What is going to go below 21? Anybody got an idea?
3.
What do you think?
3.
3. 21 divided by 3, what does that give me? 7. Do I need to keep working? No, I do not. These ratios are not congruent, so their sides are not proportional. These triangles are not similar. If you did keep going, you would do 32 divided by 4. That gives you 8, proving once again that I just wasted 10 seconds of your life.
7, 8.
What's up?
So how do you rotate the triangle to be the same?
It looks like this one was probably a reflection. So if you take this and you reflect it up, you get what I'm saying here?
Oh, I see.
A reflection. Take this, reflect it up,
And then dilute
and you
it.
can draw it out like this. 21, 32, 45. So it's trying to identify how the triangle was changed.
Yeah, what I did is I just rotated it, and I thought 32 would rotate.
But if you rotate it, will that fix the orientation? Is there any way you can rotate that to fix the orientation?
No.
Because if you look here, this is the longer side. Isn't that the longer side? You see what I'm saying? So it would have to be a reflection. Questions on this? Yes or no? What's up?
I still don't understand why you did 21 and 3, not 4.
Okay, well let's look at this. Look at the larger triangle. This is easy, right? So we've done this and we've done this. You with me? 45 and 5 were easy. And here's what I want you to look at. You have two sides here, 21 and 32. Which one of these is smaller? 21 or 32?
Same.
No, I'm just saying look at the numbers, 21 or 32. Okay, then which one of these is smaller?
3.
Oh, 21 over 3, 32 over 4. You see it? Yes? Or you could do a reflection mentally. Just flip the whole thing on its side. No? You okay over there? All right. Questions? Questions? Questions, answers. So, last but not least, obviously, we always end up coming back to the same thing. Similar triangles, missing measures. We know from SSS similarity that in similar triangles, the corresponding sides must be proportional. So we can use that wonderful knowledge to find the missing measures of triangles, such as this one and this one. And to do that, we would set up our old friend, a proportion, which is basically just two fractions that you set equal to each other. And to solve it, you cross multiply and then, anybody? Divide. It's in there. It's knowledge. It's tucked away. Oh, wait for you to write that in, and I want your eyes on here. You look at this first example, and I want you to look closely. How many triangles do you see here?
2.
2. There's one big triangle, and then inside it, little teeny tiny baby triangle. Down here, how many triangles do you see?
2.
2. Big triangle, little teeny tiny baby triangle. And we're trying to find the missing measure. This gets tricky if you're not able to identify the proper side length. So we look here. In this scenario, we're trying to find the height of a tree. We're going to say that this is a tree. And in front of that tree, someone is standing. His name is Enzo. Enzo is casting a shadow. And the tree behind him is casting a longer shadow. And our job is to try to find the height of the tree. Well, ask yourself a question. Do I know 1, 2, 3 out of 4 things? Yes or no?
Sure.
Yes, I do. I know Enzo's height. I know Enzo's shadow. He's 5 feet tall. He casts a 6-foot shadow. I know that there's a tree here. I do not know how tall that tree is, but I know that overall that tree casts a shadow that is 21 feet long. So I can use proportional reasoning to find the missing measures. Here I've taken those triangles, broken them apart. So now you can clearly see I have Enzo standing here, casting a shadow. 5 feet tall, 6-foot shadow. Here I have my big, beautiful tree. Hello, tree. Casting a shadow that's 21 feet long. When you set up your proportion, you must be very careful. You must categorize your stuff correctly. I always like to take the larger triangle and then set it equal to the smaller triangle. And make sure you set up your numerator and denominator correctly. Please focus on this because there's lots of different ways to write this. Very few of them are correct. Many ways to get this wrong if you set it up correctly. On the top, I always want to put the height. Enzo's height tree's height. So we're dealing with the large triangle, also known as the tree. What is the height of the tree? Do we know it, yes or no?
No.
No, so we're gonna put X. How long was the tree's shadow?
21 feet.
21 feet. So let that sink in for a while, because when you write your next fraction, you're gonna set it up the same way. The small triangle represents Enzo. Height over length. Height over length. Always the same way. So, how tall is Enzo?
5 feet.
Is that gonna be your numerator or denominator?
Numerator.
Numerator. So 5 over what? 6. And then you cross multiply and divide. In case you forget how to do this, here's what you do. You cross multiply the two numbers located diagonally across from each other. We did this earlier in the year. Quick review. 21 times 5 gives me
105.
105. If you take that and you divide it by 6, what do you get?
17.5.
17.5. And we include the unit feet, which means that I found the height of the tree. The tree is 17.5 feet tall. Before we do the last ones, anybody have any questions on the first one?
No, sir.
Notice, I did you the favor of splitting the triangles apart. When you're solving these problems, you won't have that. You may just have a diagram like this, or you won't have the diagram. You'll just have the word problem, and you'll have to draw your own diagram, so make sure you identify what it is you're doing. We look down here. Looking at these two pictures, this graphic and this graphic, does anybody notice one major difference between the two pictures? Not numerically. Anybody notice a major difference? Something that could be a little hiccup for us if we're not careful. What's up?
The platform looks bigger in the second picture.
Yeah, but something. Hello?
On the bottom for the base, there's 2 numbers.
There's 2 numbers on the bottom. If you look here, I mean, there were 2 numbers here, but this long thing right here gives us the length of the entire large triangle. This little number 6 here gives us the entire length of the small triangle. When we're looking at this one, and I really hope you're paying attention to this, you are given the length of the smaller triangle. How long is it?
54 feet.
54. But to get the length of the whole big triangle, what do you have to do with these 2 numbers? Good. Add them together. 40.5 and 54. You add those 2 numbers together, and what do you get?
94.5.
94.5. So be careful when you do that. That's a real troublesome area for people. Always make sure you're getting the entire length of the big triangle and then the length of the smaller triangle. So we take those triangles, we split them apart. We know we're going to add those 2 numbers together, and we start setting up our proportion. Colton, large triangle, what is the height? 35. What is the length? Good. 94.5. Excuse my handwriting. Actually, hold on. Did I put this here? I could have sworn I did. Sorry, people at home. Hello. Hello. That's much nicer. Okay. Thank you. Never mind. You missed it. All right. Azanza. Small triangle. What's the height? X. We don't know it, so we assign a variable X. And what is the length of the smaller triangles? Good. Then we cross multiply 35 and 54, divide it by 94.5. Autumn, what did you get? What? Somebody already did it. What did you get? 20. Survey says he's right. Congratulations! You're the big winner today. Good job. 20 is correct. Oh, sorry, I made it ring.
You should put 20 feet.
20. Good job. 20 feet. Don't forget to put the units. 20 feet. What's up? Questions? I have a question in the back. Yes. What's up?
You multiplied the 54 times 35, right? Or
Hold on 1 second, please, class. I have a question. So what I did is I cross multiplied. I always multiply the numbers located diagonally across from each other. I multiplied these 2, and I divide by whatever's left. Same thing I did up here. I cross multiplied 21 and 5. The only number I didn't use was 6. I divided by 6. What's up?
What is the X of this value?
Doesn't matter. You cross multiply whatever numbers you have. So doesn't matter how you set this up. If you're given number X equals number. You're always going to cross multiply whatever numbers are located diagonally from each other. And you would divide by whatever number is left.
So if it's on
And that's
top.
going to give you X equals whatever.
Whatever they talk like that.
Could be. Remember, you're just always cross multiplying the diagonal numbers and dividing by whatever numbers left.
Keep it fun.
Any questions?
No, sir.
Questions? Okay. Don't forget to like the videos, leave a comment, share it with your friends, and of course, subscribe.